enjoy it and also...
Hola. Ante todo, muchas gracias por venir. Y lo primero, un aviso, y es que voy a hablar un poquito de matemáticas.
Video and audio software for the real house, and it was a small company. There were 4 programmers, and we got an award to the best European software of the audiovisual environment because we were the first ones to broadcast directly from a mobile phone. That was the time where the mobiles were very rudimentary, and from then I moved on to programmers, and I worked on military software, specifically multilateral versatility program, which is basically the way in which the NATO countries exchange data in a secure way. And from then on, I moved on to Sopra, working as an architect to the MDS project of the Airbus A400M. And I discovered that I like innovation, and I started doing quite a lot of innovation work in Sopra, and I moved to AXA. And I've been there for a while doing chatbot, computer vision, AI, or IE, everything that's sort of far away from Java. On the other hand, I organize meetups on Yes, and I participate actively. I've done some code pushed for Node, and I organized another con from Barcelona. Like this, but much smaller, and talking about Node. So why am I here? This is my current work, which is about doing neural networks and computer vision of things that are a bit sort of not standard, and there are no suppliers for instance, to find the angle of a car, to know when they send pictures from a car whether all angles are being covered. And this was one of the projects. This was to give a DNA and a document to find the signature and compare them. It's not what an expert in signatures would do, but it's good enough to be comparable to what human beings can do. And we started with problems because problems come in PDF or whatever, and the signature can be on top of printed writing, or the questionnaire may be written handwritten. And with different problems we got here, but my question was, who ensures that nobody has manipulated the images we're receiving so that we do not see the signature, but artificial intelligence believes there is a signature there and both match? That would be a huge problem, that you cannot see the signature visually, but the computer vision says it is there. So I ask myself, first of all, how many of you work in a company that deals with computer security? Many of you. How many of you are in a company that you do pen tests of computer vision systems? No hands there. So this is what I found, that we are very much focusing on transfers, communications, pen test, and nobody is realizing that there are more and more artificial intelligence systems, and nobody is testing this. And there's no company that gives you the service of pen testing a computer vision system. And at some point, I thought about morphing. If we do a facial recognition system, I I stop seeing the first character and end up seeing the second one in frame 7 approximately. That was in. What about computer vision systems? Do they do that at the same speed? Well, that's not the case. When you train them, they tell you whether a picture belongs to one phase or the next one, and they switch the point at which the computer vision system recognizes that a frame is from the face of one of the players is not the same one then in our case, because we look at some things and the computer vision recognizes features, certain characteristics of the pictures. And why? Because there are vision computer systems that are being used already, particularly in self-driving cars. And if you move in the military environment with a military drone, self-driven and with weapons that can fire, what happens if somebody managed to fool them? If you have armed systems that have computer vision, you have to be very careful because that computer vision could be fooled. Having said that, I started with my research. That was, all of this is why I started doing this research, what was my concern, and then I want to explain what neural networks are. Why? Because there isn't that much knowledge around. It is a neural network, it's just that you get inputs, we calculate weights and multiply them, the inputs by the weight, and then we add them up. That's all. And we get an activation function. What's that? It's the one that decides whether yes or not and how much yes and how much no. When I started at the university, the sigmoid was being used, but that demands a lot of computation time, and you will see that the one that's more often used now is the ReLU, which is linear, and that just says whether if the value is below 0, 0. And if the value is above 0, then you get the value. So it's very easy, very simple to implement, and requires very little computation, and that's why it's used. But the systems that it produces are more lenient because the sigmoid has a greater curve, therefore there is a greater sort of space for decision making. So that would be a perceptron. But what happens when I put many of them in? Each one of these circles is a perceptron, and each colored line is a weight. Okay, so what a neural network does is that it has two directions, a forward direction from input to output and a back direction from the output to the input. So when we train, what we do is the back propagation. That is, we tell them this picture is this or this data is this, and we tell them how when they're going wrong, and the system starts learning. And how do they learn? This is not new. This is from Newton's time. With a certain gradient, Newton, or curve, Newton devised a method to calculate the minimum of the curve, the gradient descent. So it's nothing new. And what we do is to try to look for these minimums of the loss function, which tells us which far away we are from the system working properly, roughly. So depending on how we train, we're going to find a local minimum or another local minimum or another local minimum. That's quite impossible to ensure that the minimum that we have found is actually the smallest possible one. And to that, we have to add something else. When we talk about this, there is a concept that's called the learning rate, and we can think this. You have a bigger number, it will learn faster rather than but the reading rate actually tells you, also roughly speaking, the size that of the step that you take to look for that minimum. If you take too large a step, you may be overstepping one minimum. But if the step is too small, then you go too slowly. So you have to adjust or strike the right balance so that it doesn't take 5 years to work or it's not finding anything. And what I have to the right are the different training methods, and at the end what they do is to solve that gradient descent. And The one that has been used more often is SGD. The following ones are more recent, more modern, and better. For instance, ADA Delta adapts to what you're training. Therefore, it's quite likely that the rate changes adapting to the circumstances. You're following me, right? Okay. So when we talk about computer vision, we have to make a difference between recognizing a single object or multiple objects, and in this case we have the classification, which is what's done most often in computer vision. I give you a picture, tell me what's there. Then we have localization. I give you a picture, tell me what's in the picture and where it is. Where is it? This is what I use for signatures. I have an image of the document and I have a neural network that looks where in the document there is a signature, because the signature can be to the side or at the bottom, or so I need first of all to localize it. And more complex is object detection when there are multiple objects. And why is it more complex? Because they may overlap, and what's even harder is instant segmentation, which is to give me pixel by pixel whether that pixel contains the object or not. Okay, so far so good. We think neural networks are great. When it comes to real work, it is not so wonderful. In real work, you're given 8,000 documents with signatures in different positions, and the first job you have to do is open them in a picture editor, look for the signature and mark where it is to be able to train. And it's quite time consuming, and you cannot send it to a third party because these are classified data and you have to do it in-house. This is ImageNet, which is the one that's been driving computer vision. It's a huge picture collection that they have already classified. They did that with a Mechanical Turk. Amazon Mechanical Turk is actually a platform in which you upload a problem to be solved, and that is solved by human beings. For instance, a Mechanical Turk one day sent 1,200,000 images to localize where this object was or some other object. What happened behind was that there were people from all countries defining in a program where the objects were. So it's quite painstaking work, and in the last few years there were some challenges on their data games which were better at classifying, and there were different categories for that. And the first thing is to go between top 1 and top 5. It means that you, in a picture, you say what it is and it's in top 1 and top 5, and in a picture you can say but it can be in the top 5 of things that you say it is. So there is a radical change in 2012. Why? Because until the year before, BCGs were being used, which were classical neural networks. And in 2012, AliceNet came along, which was a convolutional network, which is what's used in computer vision right now. And since there's been an improvement in 2012, AlexNet won, and since 2015, Google. And the margin of error was 3% in 2016, so below human error. And sometimes it's due to the fact that the pictures are not all right. And in 2017, we know, although it has not been publicly made public, that it's below 2%. When we talk about convolution, we ask ourselves, what does it mean? Well, it's only the product of matrices. So an image is a matrix of colors. We all agree on that, and if there's another matrix, if we multiply with the window, we're going to obtain images like this one. So a convolutional network is the one that can consider those convolutions as part of the weights. So those convolutions are calculated, and what are they good for? To detect features. For instance, here in this convolution here, we see that we are removing all colors and we're staying with the borders. So here we could see straight lines that will tell us whether this is a building, a door, etc. And if we're not calculating a feature but 200, all different, and those 200 features are the input for 400 more below. So the quantity of features that you're computing is multiplying, but there is a problem. If you have an image size n, I didn't say that, but in computer vision systems, input has a predefined size. If you decide that input is 290 by 1990, if you put in a picture, it escalates. So if all layers are done in 299 by 299, we're going to take several years to train a computer vision system. So we try to minimize the size at each step of the images to keep only the features so that it's faster and faster. So x by y is squared x by y, so you're applying the square root to the complexity. So and for that we use Boolean. Max Boolean, if we have to reduce a size to half of it, I go beyond 4 points. You keep the highest one, so 6, 8, 3 and 4. If we combine convolutions, is it that late? Okay, I'm going to have to rush. This is what the layers see. If you take a picture of this, you'll be able to see a neural network in your portable computers. And here, let's move on to the attacks. There are small attacks, large attacks and picture attacks and real-life attacks. There are many articles on that. Here, there's one that summarizes them all. And this is the one pixel attack, which is to modify a single pixel. It's working against the far, and the pictures are 32 by 32. What's happening internally? Well, that a single pixel in one picture, when you take it to 3 layers, the red to one of the images is taken to 155 and the other to 0, and that entails a huge perturbation of the size of the image that distributes throughout the whole network, and it is misinterpreting what's in the image. So this came along in August 2017. The cars have been hacked. We're all going to die. With stickers, they managed to do the face in traffic signs, and it fooled cars in 67% of cases. What's the reality? Well, this is the real big size of the pictures they were using. They were using 32 by 32. I don't even know. I don't know what's there. And they didn't actually use a real autonomous car. They did their own network, and it's a homemade network. So they weren't doing image filtering. So they were working with raw data, and they were not doing augmentation. Augmentation means from a picture to calculate several pictures to have more advanced data. Play adversarial. What's that? An adversarial is giving an input image X. The result of the CNN is a probability distribution over label. So you can modify the image to make it identified as something else. So you propose this theory, which is basically given an input image X, you have to calculate an X prima, which is the original picture slightly modified, so that it means that the probability given back by the network is Y prima. And you have to do that with a very small perturbation, and I chose 2 over 255. I don't want to move every pixel be more than 2 colors. So if you have a discriminator, it's an existing neural network. There is a generator, and the generator generates images that keep attacking. And the problem is that it's a black box system, but it takes a very long time. But Christian Zeri did that with this system by applying this perturbation to this picture, generates a picture that for us is the same, but all of these pictures here and all of these pictures here, the networks say that they are an ostrich. They discovered that it doesn't depend on the topology that you're using. They thought that it was only going to use for a certain type of topology, but whatever topology you use, the adversary works in many topologies, not all, but quite a lot. And they're not sure about why, but they think it's not due to the linearity of Redu. They are thinking that neural networks learn some master features beyond the ones that they're learning, and they tend to be present in all the networks that we train with pictures. Meanwhile, this is going to be fast. What I'm doing here is I'm taking the Inception V3 already trained by Google that they used already in Vision. And on a rooted logo, I'm saying, what does it see? It sees something strange. I can do that with a rifle. But I'll stick to the rooted because I don't have that much time. So on the network that I already have trained, rather than using a black box method, I'm using a white box. So if the network is already trained and I already have the gradient descent, I pick another label and I'm going to modify the picture gradually in a random way, more or less. You see the training here? And you see how the LOS goes down until it tells me that the rooted logo is hot dog. But there's a problem here. And that is that it's not robust in rotation. But for my example, the one about signatures is robust enough because we do not get several images. And by attacking just one, you can already fool the neural network that only identifies one image. So for rotation, it can be done, but since I have a CPU and no GPU, but it can be done, and I can make a rifle look like a hot dog for the machine. How do we do that? We knew that P of Y prima had to have the minimum value, but now the P of Y prima on transformation of X prime has to be the minimum of the gradient descent for the transformation distribution that we have. This can also be programmed, but it's more time consuming. Something else that I found as I was doing this experiment is that images that are black on white, for instance, the true logo of the rooted cannot be perturbed. Why? Because we have the limitation of 2 colors per pixel. And if you have something that has only 2 colors, getting a perturbation for the machine to believe that it's something else, the machine will notice you. That would be perceived by a human being, and that's what we don't want. So pictures in black and white, only 2 colors or very few colors, and this is not going to work. A cat with quite a lot of colors around here. So doing the test on the signature itself, I see that when I'm attacking the DNA, the identity piece, it works because there are colors behind that I can modify without anybody notice, and I can fool the machine and say that there is a signature. But in a white paper, in a form is quite more complex. If the quality in the picture is not bad, maybe you could do it, but it would be a lot more complex. And you go beyond that. You can go beyond that. These people, the paper is at the bottom, can do 3D models that it's not only about 2 dimensions but 3 dimensions in their neuronal network, and believe that this turtle is actually a rifle. So here, this is my question. What do you think it's more dangerous? That if we have a defense neural network, that a guy with a rifle can be interpreted as a turtle, or somebody with a turtle can be considered a rifle? Because if a guy comes in with a rifle, we know what he's up to, and everybody's going to see that. But imagine somebody giving turtles to the kids at the entrance of a school. And this is a thought experiment, or a concept test that was done when it was said that we were all going to die. This is said is not very smart, and what's around it? It's a salt made circle, sort of a bit of esotericism here, and it has not been proven that in real life this attack can work against the Tesla. So far we seem to be safe. That's all. Questions? Hello? I have a question with these neural networks, or rather the computer vision network, which is so trendy in China right now with face recognition. Is there any device or technology that can make the distortion in real time? That is something that without you touching the screen can actually distort the image that the machine is seeing from you. Yeah, the example that I've given you is that has taken a few seconds. It's working on CPU, but with the video, I'm not saying that it's going to go by 20 frames per second, but perhaps 4 frames per second as to face recognition. One of the examples that there is about generative adversarial networks is that that you're generating random faces. There is something that generates faces, and that the facial recognizers say, yes, it is a face, and they can tell you whether it's smiling or looking sad, so the technology is there. No more questions? Okay, thank you.